Hey class, this is an optimization problem. And so one of the things that we want to know right before we even start the problem or read into it is milliliter. 1 milliliter is the same as 1 centimeter cube. Okay, so what this is saying is that the volume of this POG can volume is 340 centimeter cube. So that is, I think, our restriction. So the question is asking what's the dimension of this POG can to minimize the cost of producing the can, right? The cost of producing, we want to minimize, well, when we are producing the can, what do we worry about? What geometric property? We want to minimize the surface area because that's the material that you have to use. How much material you have to use is the surface area of the can. Okay, so let's take a look here. We have a cylinder, right? We have a cylinder. So the dimension here would be R and H. Okay, so then the volume is pi R square H, volume of the base shape, which is a circle, multiplied by how tall. Pi R square H is 340. And then the surface area is going to equal to 2 circles, right? So 2 pi R squared. And then this part right here, the wall, when you open that up, that is a rectangle, height H. And then this part right here comes from the circumference of the circle. So that is 2 pi R. So then the area here is 2 pi R H. So we would have to add 2 pi R H into the two circle, the top and the bottom. Okay, so that is something that the function that we are going to minimize. However, it has R and it has H. So wouldn't it be nice if everything is in terms of one variable? So what do we want to do? Solve for R or solve for H? Well, H is only here once, so I think I'm just going to go and solve for H. So that would be 340 divided by pi R squared. And I am going to use that to substitute that into the H here. So then the surface area in terms of R only is 2 pi R squared plus 2 pi R multiplied by 340 divided by pi R squared. And when we reduce that, the surface area in terms of R is going to equal to 2 pi R squared. Pi cancel with pi and R cancel there. So I would plus 680 divided by R. That's the function that we want to minimize. And in order to minimize, we need to first find the critical point. And to find a critical point, I need to go ahead and take the derivative. So that would be 4 pi R minus 680 divided by R squared. And the critical point would be when the derivative is undefined, which in this case is R is 0, but R cannot be 0 because that's the radius, right? If R is 0, then you don't have a can. So R cannot be 0. So this function is going to be defined in context, that is. And then the derivative is equal to 0 when critical point happen when this 4 pi R minus 680 over R squared is equal to 0. That means 4 pi R cubed is equal to 680. So R is equal to cube root of 680 divided by 4 pi, and that is cube root. Okay, so R, when you calculate this, it is approximately 3.78 centimeter. Okay, now we need to confirm that that critical point is going to give you a minimum. So how do you do that? You are going to go and find the second derivative. I'm going to use a second derivative test because in this problem it is easier. The second derivative is going to be 4 pi plus 2 times 680 is 1360 over r cubed. And so this is always going to be positive. So your function concave up, which means right there you have a minimum. Okay, that's how we use second derivative test. If the second derivative is positive, then the function is concaving up at that point. That means you have a bottom or a minimum. So we just confirmed that that is the minimum. R is roughly 3.78. So if that is the case, then H is going to equal to 340 divided by pi multiplied by this right here, cube root of 680 over 4 pi, and then square. That is H. That's the exact answer, right? This is R, and this is H. But if we want to get an estimate, we'll have to type that into our calculator. So let's put that in the calculator and see what that is. So decimal tells me that this is approximately 7.565 centimeter. Okay, so what dimension will give this can the minimum surface area? It would be the radius would be roughly 3.78 centimeter. And then the height of the can is 7.565 centimeter. And that is the solution to number 10.